Okay, I'm going to talk about marine stratocumulus clouds, and so we're down a little bit closer to the surface than we have been so far in the first two talks. And my interest in these and our interest in these has been sort of a long-term project. It started out back in 1976, I guess it was, but let me just give you this introduction here too, that one of the things that we see, of course, is that we see lots of aerosol cloud interactions, or at least aspects of that, when we look at the satellite imagery. And here's just a sort of nature's way and man's way, as I call it. And the ship tracks here are good evidence that there's some modification of the clouds that's probably associated with aerosols. Less clear as to what the aerosol roles are in the pocks and rifts just by looking at it, but we'll talk about that a little bit later. So just a little bit of a history, as I said. 1976, I was a graduate student working with actually Doug Lilly and Wayne Schubert at that time, and they had 5 flights with the NCAR Electra that we got to fly out over in the first time looking at some stratocumulus clouds. And part of this was stimulated by Doug Lilly's work with the simple mixed layer model of stratocumulus clouds. It was in 1969. And sort of the awakening here, though, when we got out there on this one flight, was the drizzle on the windshield flight. Now, this was before the real-time displays of cloud particles and everything else going on, and we're going in these little wimpy clouds. They're a couple 300 meters thick, and we've got rain, or drizzle at least, in these clouds. So as that sort of that point, we did realize that maybe cloud microphysics are important in this whole process, and that it's not just simply a mixed layer where the turbulence and everything else pretty well takes care of itself. And you can see just from the satellite, this is a satellite image, just the natural variability is fairly large too. So Doug Lilly, he was the one really coined this idea that the marine stratocumulus it's a great natural laboratory because the synoptic variability is weak, and you have these nice uniform cloud decks, except that there is a certain level of natural variability within these clouds, which does complicate this problem in terms of a natural laboratory. And we even speculated that on these cloud trails that one would expect sort of a narrow droplet distribution, less drizzle, and enhancement of the cloud. We didn't have measurements on this particular flight in the cloud trail itself, but after realizing what we were sampling compared with some of the other clouds, we had sort of speculated on that. And since then, there have been different studies which have been done to look more carefully at these ship tracks in particular. And I call these sort of reactive, inadvertent probing because it's hard when you're out there and you get your airplane ready to go and you fly out and you have to find a ship track. There may or may not be one there. So it's always a difficult problem. But in the MASS, which was the Monterey area ship track experiment I guess it was in '94, they were able to make several aircraft penetrations and characterize the aerosols. And here's just an example showing here from the ship track. We can see that the cloud droplet concentration goes dramatically higher in the ship track itself, as with the aerosol concentration. Droplet radius goes down, albedo goes up, so consistent with the Toomey type approach to that. Since then, there have been several satellite studies, and Jim Coakley, of course, has been hand in hand with that. So we have new tools now which can also help use these. But again, this does serve as a natural laboratory because there's clouds out there in our ships, and so we have these ship tracks that we can study. And I won't go. Here's a more recent study that was Christensen and Stevenson have done, where they've actually used Calypso to look at these ship tracks and look at the processes that are going on there. As far as the natural variability, how does that affect with the aerosols? Again, a little serendipity here that we had a chance to fly across one of these rift or pox areas that you can see here. It was just off the coast of California, and flying along in this direction here. Fairly solid clouds, more broken clouds. And the interesting thing is if you look at the CCN concentrations, that they're 50 to 60, so that's still pretty marine, and there was some drizzle at the top of the clouds. But if we go into this area here, the CCN goes way down. In fact, there was one where the CCN went to 0, and Hoff Janssen was hammering the instruments, and the ultrafine went way up, and so there was new particle production and everything else going on. So these clouds can be very efficient cleansers in some cases, and I think there's some further evidence of that in some of the more recent studies that have been done on here. And of course, here's Danny's work where he looks at some of these variations in the stratocumulus clouds that may be associated with the aerosols, and he has his ideas on how that works. More recently, the Vocals regional experiment, this is Rob Wood was the lead scientist on this, but it gave us an opportunity to look at some of this natural variability and also some of the man-made pollution sources as effects on stratocumulus clouds. And this was in 2008, a very successful experiment. And you may have heard Rob's talk yesterday. One of the things they were looking at these pox areas. And again, they have found, here's just showing the same open cells, closed cells, and here's with the Wyoming King Air radar showing the difference in the characteristics of the clouds in these different areas. And they were also able to find these very large differences in the aerosol concentrations with some ultra clean, very clean air along some of these edges of these clouds. So I would point you to the paper that Rob, he presented yesterday, and there's also in the Atmospheric Chemistry Physics Journal on this. The other part of this from the Vocals perspective is that there are these natural sources, or the unnatural sources, I guess is the other way to call them, or man-made sources of aerosols. This is a MODIS image showing the droplet concentrations in the stratocumulus cloud, and you can see this area in here, which looks as though it's being affected by a couple of things. Santiago has a source of aerosols. There's also these copper smelters along the coast here, so it was speculated before Vocals at least that they were contributing to these aerosols and thus modifying the clouds in that area. So we took advantage of that. We used again, the Surpass Twin Otter, and we had a very, we don't have much range with that aircraft, so we ended up going to every day to 72 west 72 and 20 south. We call it Point Alpha because we by name. And just to show you how consistent at least some of the boundary layer structures are. I know that normalize the cloud top height here, but in general we found a very, very consistent boundary layer structure. Here's some moisture above, and so some of these cases. But there was a rather large variation in the liquid water content of these clouds. But again, pointing to the fact that we can use this as sort of a laboratory in a sense that we don't have a lot of variability, at least in the boundary layer structure. But what's interesting, though, and that the liquid water path, the red points here are from the aircraft, and the other points here are from satellite estimates, from GOES satellite estimates. And we did find that there was this relationship, liquid water path versus CCN concentration here. I'm not going to try to explain why it looks like that. And also points out that there are other things which do affect the liquid water path and the aerosols in unison, so one has to be careful in this natural laboratory in understanding how this works. So we're trying to dig into this and understand that. So again, the case. So that takes us to a little more, a different idea was the more proactive, what I call proactive probing or cloud seeding. And sometimes we've tried to avoid the use of words like weather modification or other things when we're doing these experiments, but so we call it proactive probing, I guess, or cloud seeding. But anyway, this may look familiar to some of you. These are flares on the backside of an aircraft. Sometimes when I show this slide, people think the airplane is on fire, but it's not. And we actually did some seeding in this little area in here. And this was these flares of Rulof's had some description of these flares and the characteristics, and Dan Breed has been associated with aspects of this. So the idea is that these ice flares put out some larger salt aggregates which serve as giant nuclei. And our idea here was to see if these giant nuclei could change the droplet spectrum and in the way that the theory is thought. And so there are some ideas that the drizzle starts in these clouds due to giant nuclei, but it's always hard to do that in a natural laboratory because it's hard to sample those things from natural processes. So our strategy here was, we had tried this a couple times and without much success, but we found the key was we made two lines here of flares. And initially we had done this with one, and it was always difficult to say, well, did we do something or didn't we do something? And the nice thing about the flares is they, in addition to the giant nuclei, they also put out a lot of small particles. And those were fairly easy to see in the PCASP instrumentation. So the people on board the aircraft could actually track the PCASP. And in doing so, if you look down here, we could see these peaks. And the key was we saw two peaks. So every time we saw two peaks, we know we were crossing these two plumes. So the plumes are advecting with time, so to keep track of where we were going. So you can see this kind of a strange pattern that we flew around here, probing these two tracks as we're going along, using the PCASP as the markers. And the nice thing about this, compared to some other ways in which you have to do seeding experiments, is we have the background right there. So here is the droplet spectra in the background here, so that's well characterized. And I'm just going to show some of these later. Here's 14 and 15. So this is actually the same plume. It's just being sampled as the aircraft comes around and samples it again here. And you can see the broadening that has occurred here in the droplet spectrum, and we attribute that to the addition of the giant nuclei in this process. And here's just another way of looking at it. Here's the cloud effective diameter from the beginning here. Here's the background, and we also the cloud spectrum width you can see is sufficiently enhanced here. One little bit puzzling part of this is that one of the plumes showed this and the other one didn't, so we haven't explained that exactly. But another thing to look at is the volume of the volume ratio of the 20 to 40 micron drops. Compare that with the background, and you can see in this plume that ratio goes, here starts out near 1 during the first plume and continues to grow as time goes along. So we are encouraged by that, and this was more of a demonstration as much as anything else. And the idea here is that we have a nice stable background. So even though there is variability in the clouds, locally it can be fairly constant. So we were encouraged by that. And we saw this clear evidence of broadening. So we had some ideas for some potential future studies, and I'll talk a little bit more about that as we're going along here. Now, cloud seeding has also been suggested as a geoengineering. The idea is to add CCN and brighten these clouds, and the clouds that would be most susceptible to this, of course, would be these stratocumulus clouds and other marine clouds. I'm not going to discuss the merits of this idea. As you may have seen this idea here that these droplets would be produced through fine sea spray, and that those would then, in a sense, be the source of CCN that would brighten the clouds. So while there's many aspects of this issue that I think need to be looked at very critically, and I think in that respect that the stratocumulus clouds do give us an opportunity to do that. So we've have some future plans here, and this is coming up in July of 2012. And the idea is here we call this controlled aerosol perturbations in marine stratocumulus clouds. And the idea is to test some of these ideas. We're going to do some CCN seeding from ship for cloud brightening and drizzle suppression. Some giant nuclei seeding, again, a different idea here, looking for cloud droplet broadening and drizzle production. Controlled ideas, a little more controlled seeding in terms of the size, composition, concentration. I say that a little bit, not quite as controlled as we'd like, but at least we can characterize some of these aerosols. The effects of background aerosols on cloud response is important. We know that in certain conditions, for example, with a giant nuclei, if we have a cloud that's precipitating low CCN concentrations, that the giant nuclei are probably not going to have very little effect. At least the modeling work that Graham Feingold and Bill and others have done has indicated that. So the same applies to the application of the CCN themselves. So we're interested in that and in understanding how the background affects these responses. And of course, there's other issues here which come up in terms of if we have CCN sources near the surface in a well-mixed boundary layer versus a decoupled boundary layer. Of course, these processes are very different, and so we need to understand how that works. So this is what we call this seeding for science. The key here is cause and effect. It's so difficult if you're using satellite or if you're going out in the field how do you establish cause and effect? And so the idea here is to produce a source and then try to better understand the cause and effect. So here's just a little idea of how this will work. The dispersal will be from a ship that will be off the coast, and this is a picture indicating this is one of the ideas is to do a pattern like this. The Twin Otter will be the aircraft that will be used. We also, from the aircraft itself, we have a way of dispersing giant nuclei, which I'll talk about in a little bit. And another key part of this is that the Twin Otter now has equipped a FMCW cloud radar, which is very sensitive to large drops and drizzle. And so this will also be a very useful tool in characterizing whether drizzle is being suppressed or produced or how that's being modified. In addition, on that aircraft, we've also developed and tested actually a technique for putting out radar chaff. And the chaff is cut to 3/4 of a millimeter, so it has very slow fall velocity, but it's optimized to be seen very well with a 3-millimeter radar. It's a quarter wavelength. And we will use this as basically as markers. So sometimes it's hard to figure out when we put down these lines where we really put it down, but we can use this as a marker that can then be detected by the radar. Well, here's the smoke generator that Lynn Russell has rustled up here. This is not on a ship right here, but this is going to be our CCN generator. Not very pretty, but apparently it makes a lot of smoke and dust. And you can see why. I guess this is used by the military. That's why I forgot to mention that, but it's pretty obvious. The other, for the giant nuclei here, we owe this to Danny here, and he has his milled salt, and here's some of his pictures that I've shown here of here. So to dispense that, we've developed what we call a salt machine, and so this is sort of a farmer's engineering project, the way we've done this. But we have the salt is in here, and we then have an auger feed, so we can adjust the feed of the salt into a fluidized bed where we have a grit in here. So there's a flow in here, which the idea is that the grit itself will knock apart any of the salt particles that are sticking together or do anything else. And then it's ejected out this tube here, so we can eject that out the window. So we can, in this way, do some adjustments to it. Have not tried this on the airplane yet. Hoff Janssen has tried in his lab. Initially, he had the hose going out the window. We were making a nice salt cloud, but in later tests, I understand he did it without that, and he filled up his lab full of salt. So you do have to be careful with the salt too, I guess, because electronics don't really like it so much in some cases here. So anyway, this is our plan. Well, okay. So now a little speculation here. So I'm going to end up here pretty soon, and. One of the problems that we see, in the stratocumulus clouds themselves, a lot of times there's a lot of mesoscale structure. And so there's been a lot of arguments that the mesoscale structure itself is being modified, the aerosols here. So we said, well, maybe we need a large-scale seeding cloud clearing experiment. And here's some possible candidates for doing that. Here's a 747 that's been equipped with this is fire retardant here, but it's very hygroscopic as it turns out. And this is just water here, and I know water has been used as a seeding agent before. So anyway, this is probably not serious that we should be looking at that. But there is this curious idea as to why those pocks and holes grow. And I think that, we'll stop there. And the last thing I want to show here is that the salt machines are not a new thing. And I showed you this one, but this picture here is you may have seen this one, Hark. This is the rain machine that was put on in Hawaii, and the idea here was that there was a boiler in here that actually was run by propane, and they would shovel salt into this, and the idea would be ejected and lofted up and salt the clouds and increase the rain here. So. Salt machines, it's an interesting proposition, and I think the marine stratocumulus clouds do offer us an excellent laboratory for testing some of these ideas, and hopefully the next time I talk I can report on what our results were from next summer. Thank you.
Questions or comments?
Bruce, yeah, very interesting.
From the ship that you're flying to, you get summer.
Right.
How the smoke generator is it very hygroscopic? And how well characterized?
Lynn is working on that, so we're going to try to characterize that before we get in the field. And her sense is that it's probably going to be similar to the effluent that comes from a ship stack. That's the idea. Now that hasn't been fully characterized yet. So we are considering other options too for making CCN. But
has anybody done the carbon? Because it presumably produces a lot of that carbon, right? So it's absorbing, especially in droplets. So you wonder whether that's also going to play a role in that.
Yeah, I'm leaving that up to Lynn and John Seinfeld, and that's their job to look at that. We're also looking at some other CCN sources in terms of the flares. So, but we haven't finalized anything on that. So there's other ways to do that.
So.
Actually, calculations that we did show that up to about 500, 600 cloud droplets per cc, the effect of giant nuclei is really minimal. So if in your stratus clouds across Chile you have relatively low concentration of cloud drops,
right.
If you want to do artificial change, probably the best thing to do is first increase the total concentration and then add the giant ones. So the size distribution of your flares should have should be a wide distribution.
Right. Okay. So that's a good thought too. So.
Yeah, I remember there was a randomized ground-based salt seeding project in India, and I don't know what they used for generators, but that might be something to look into, actually.
Yeah. I've heard there's various techniques.
Yeah.
It involves people shoveling salt out the back of an airplane or something like that.
I've seen some of those planes.
Just lift it in the air, whatever fell down.
Yeah. Yeah, well, I won't even tell you about our adventures in Chile where we did some salt experiments, but anyway, so out the window. So.